Each tunnel segment weighed more than the equivalent of 24 space shuttles. Between them, they contained enough concrete to build a pavement around the Earth twice. No machine in the world could lift one into the air and put it into place. And these engineers had to get each 55 million kilogram piece off dry land and into the middle of the Øresund Strait. The answer was to turn them into rafts and sail them. First, any holes were plugged with giant steel plates, each weighing more than 3,000 kilograms. These enabled the gigantic concrete structures to float, but there was still no way to transport them to the water. So an ingenious lock system was built to bring the water to them. The end of the assembly line was surrounded on 3 sides by dikes. The fourth was closed by a huge movable wall, and the basin was flooded to more than 9 meters above sea level. It took 100 million liters of water. Even when afloat, 4 23,000 kilogram winches were required to move each segment, and 2 more winches to steer it to the deep end of the basin. When the water returned to sea level, the segment was ready to head out. Then, when it was over the trench, there was a new challenge: sinking it. Forcing a raft this big underwater was not an easy task. The trick they used was ballast. Water was pumped into special tanks very slowly and evenly to keep the segment horizontal. 4 massive cables helped guide its descent. Precision was paramount, so it could be accurately connected to the rest of the tunnel. Winch operators used GPS and depth gauges to make sure they kept on target. The margin of error was less than 1¼ centimeters in any direction. Divers installed a temporary frame to help guide it. Then, when it reached the seabed, winch operators pulled it tight against the previous segment. Any seawater trapped between the segments was pumped out. The steel panels were removed, and to keep the tunnel from ever floating again, concrete, almost a meter thick, was poured the entire length of the roadway, then boulders piled on top. The system worked flawlessly for the first 12 tunnel segments, but the 13th still got special handling. It was officially numbered 12A for superstitious reasons, but unfortunately renaming it wasn't enough. On Tuesday, the 4th of August 1998, wind and current conditions in the channel were perfect. The tow-out of the new tunnel element started uneventfully. By midday, element 12A had been guided into position. At 3:30, pumps added ballast, slowly sinking the unit beneath the waves. Then, suddenly, something went very wrong. The segment started to tilt, and then collapsed. A huge explosion of water blasted 30 meters into the air. The segment plunged to the bottom. Crews on the pontoons shut down all power, fearing they'd be electrocuted. It was hours before they figured out what had gone wrong. The verdict was human error. A steel plate hadn't been sealed correctly. Water pressure had forced it open and flooded the segment. The winches weren't able to hold the added weight. Luckily, no one was injured. But what about tunnel segment 12A? Extensive testing confirmed it was still usable, but valuable time had been lost. Øresund's builders could have chosen a different method to build their tunnel. They could have bored a tube under the seabed. This is what Denmark did 2 hours away from Copenhagen, where rail and road needed to cross a channel called the Great Belt. This was the site of a disaster far worse than the Øresund's. To dig the 2 train tunnels, they brought in 4 enormous boring machines, each 90 meters long. The front end is a drilling head weighing over 100 million kilograms and measuring 7 meters across. The cutting head chews up soil and boulders. An auger shuttles the ground bits to a conveyor belt, and they're dumped on a small train. As each tunnel boring machine worked its way underground, it also installed pre-made wall segments, 62,000 of them. The problem with boring was that the ground could be unpredictable, and this was how disaster struck the Great Belt. A boring machine hit a water pocket. At first, water began to drip in. Then it started to pour. A special safety hatch should have contained the flood, but it had been left open. Water flooded one tunnel, crossed through the emergency tunnels, and flooded the second. It took a year to get the project back on track. The tunnel here differed from the Øresunds in another way. It went right across the channel, so heavy trains wouldn't have to use a bridge at all. This gave engineers more design options than they had at the Øresund. They were able to build a suspension bridge, and they did so in a big way. The second largest in the world, spanning nearly 2,700 meters. The towers reach up 250 meters, almost 30 meters taller than the towers on the Golden Gate Bridge in San Francisco. Unlike the Øresund, this bridge's structure depends on two main cables draped over the towers. These monster cables are almost a meter thick and around 3 kilometers long. The main cables are actually made up of over 18,000 wires, each thinner than a pencil. They're not twisted together, instead they're stretched next to each other and bundled. The finished cables weigh over 9.5 million kilograms each. The trick to making a suspension bridge is anchoring each end of the cable. For the Great Belt Bridge, the anchor blocks were enormous, little islands unto themselves. Each weighed more than 300 million kilograms. Cable-stayed bridges like the Øresund don't have anything like this. Anchor blocks are just used for suspension bridges. But the cable can't just be buried in the concrete. It would pull right out. The load has to be spread over a large area. So as the cable enters the anchor block, the wires branch out into smaller and smaller clusters. By the time the Great Belt cables reach concrete, their load is spread over 64 square meters. It's easy to see the cable's flexibility in the anchor block.
It would take a little time but it will actually start to move. Now it's moving a little, 3 or 4 millimeters, but it's moving all the way from the top and down to the anchor plate.
This was exactly the kind of flexibility that the Øresund Bridge needed to avoid. It had to be rigid in order to carry the tremendous weight of car and rail traffic. And it needed awesome engineering if it was going to break world records. Having to build the bridge section this high and this huge created the biggest challenge of the entire Øresund project. Engineers were hurtling full speed toward the I-2000 deadline. The last stones had been placed on the artificial island. The tunnel elements had been sunk. Now it was time to build the world's longest cable-stayed bridge for car and rail. Construction began with the towers. At 60 stories, they would be by far the highest freestanding double-legged bridge towers in the world. 2 giant legs would be connected by a massive crossbeam just below the roadway. Above the deck would be open space. There were 2 reasons for this lack of crossbeam above the road. It kept the bridge design looking clean. If an animated disaster were ever to become reality, freestanding towers would help the bridge survive. Without a crossbeam above the road, the towers would be more flexible. In the event of a crash, less of the impact would be transmitted to the rest of the bridge, and it would stand a better chance of survival. The building of the towers started on land. Like the tunnel segments, the foundations were made in a dry dock. They were enormous, the base of each covering 1,500 square meters. Their dead weight was over 18 million kilograms. This was a lot lighter than the tunnel segments, but moving them was much trickier. They were 22 meters high. The Øresund Strait was only 7.5 meters deep, so they couldn't be floated like a raft. They had to be carried. No vessel existed that could do this, so the Øresund engineers built one. They started with 2 immense barges, then connected them at both ends to create a kind of catamaran. It took 5 enormous tugs to tow this contraption into the channel. At the bridge line, the foundation was lowered into a pit that had already been dredged into the seabed. GPS helped guide it to within 8 centimeters of its target. At this stage, the foundation stuck out of the water by just 3 meters. Soon each stump would grow another 180. Each embryonic tower became its own self-contained construction site, outfitted with enough equipment for a small factory. One always stayed 12 meters ahead of the other, so the massive cranes didn't get tangled. When the towers reached 44 meters, it was time to add the crossbeam. Then, at about 80 meters up, a steel box to hold the stay cables was integrated into the leg. Another box was added every 12 meters. From the outside, the towers look solid. But in fact, they're packed with equipment, including a lift. The tower reveals the penthouse view.